Okay, it's August 1st, 2020. This is the second video that's going to be on chapter 21. I'm going to have to do just one more quick one tomorrow, and then we'll be done with chapter 21. Alright, so the part that we ended up on was the DC voltmeters and ammeters. We talked about DC voltmeters and how to use a galvanometer. This would be the setup right here, and we went through this right here. Okay, so then this is what's new. This is, so I haven't uploaded this yet. Okay, I'll start uploading this before I upload the new video. So here's where we are. Okay, so this is, you don't have this unless you've uploaded it after sometime tonight, August 1st. Okay, now instead of changing our galvanometer to give us a voltmeter, say we want to change it to give us an ammeter that can measure current I, but can have no more than current Ig pass through the coil with a resistance R. Okay, now in this case, we're using this thing called a shunt resistor. I don't think your book calls it that. Everybody else does. This is the shunt resistor. So in other words, we got to limit the amount of current that goes this way. So we want this resistor here to be very, very small. A very small resistance can handle a lot of current because of what, we want to measure a lot more that can go through the coil without damaging the coil. So you got to have a lot of it go this way, and only a limited amount go this way. Okay. Now the amount that goes this way will still change. So if you have 1 amp coming in here, maybe you have 0.01 amps going in here. If you have half an amp going in here, you only have 0.005 amps going in here, half of that. So we'll still be able to set it up so the needle will move. It'll still change the amount of current that goes through here. Just that the vast majority of it will go through here. Okay, so we need to use a shunt resistor to shunt away most of the current and avoid damaging the coil. Since big R and little r in parallel, see, this is the whole this is the resistance of the coil right here. That represents the resistance of the coil. This is the shunt resistor. They are in parallel. Okay, that means that the same voltage, whatever voltage is dropped across here, the same voltage is dropped across down here. Okay, so we start off with the voltage across the shunt resistor equals the voltage across the coil. That's going to be the same. Now that means that the voltage V equals I times R, Ohm's law. Voltage across the shunt resistor equals V equals I times R, the voltage across the coil. So I is the current that we shunt through the shunt resistor. Ig is the current that goes through the galvanometer. Then R is the resistance of the shunt resistor, and little r is the resistance of the coil. Solve for big R, we get the current that goes through the galvanometer times the resistance of the coil divided by I. Suppose we want an ammeter that can read up to 1 amp, but no more than 50 microamps can pass through the coil without damaging it, and little r, the resistance of the coil, is 25 ohms. We just plug on in. We make the shunt resistor 1.25 milliohms, a lot less than the 25 ohms that the coil has. That means the vast majority of the current will go this way. We'll still have a small percentage go this way, but we can then design the galvanometer so that the needle will move up to whatever current we're reading here. Okay, we want to read up to 1 amp. We want the shunt resistance to be small so that most of the current passes through it and not the coil. Okay, so we can go back and look at some of the problems. Okay, well, this is down at the bottom. Okay, this was the one we must have already done. The voltmeter. Okay, now we're using the one as the ammeter. Okay, find the resistance that must be placed parallel to a 25 ohm galvanometer, 50 microamp sensitivity, same as the one discussed in the text, to allow it to be used as a ammeter with a 300 milliamp full scale reading. So now we want to read up to 300 milliamps, so it's going to be probably more sensitive ammeter. So we got the same thing here. These two are equal to each other. R equals little r Ig over I. got 25 ohms times the current, the maximum current we can allow to go through, and then they did a little calculation down here because the rest of it is going to go through the shunt resistor. Whatever doesn't go through the galvanometer goes through the shunt resistor, and so you get, and this is like, look at this. This is to the -1, right? It's 300 milliamps. That's 0.1 amps, or 0.3 amps. That's 3 times 10 to the -1. This is 10 to the -5. This number doesn't even show up. Okay, so it's almost like a number you can ignore. So you kind of ignore this number, and so you get 4.17 times 10 to the -3 ohms. So that's what you want your shunt resistor to be. Okay, now we are on to circuits that have both a resistor and a capacitor. So this is your voltage source. This is a switch. Okay, switch starts off open. You've got your resistor. You'd have voltage VR across the resistor. Then this is your capacitor. Now, when you first close this, let's actually read it. Circuits that contain both a resistor and a capacitor are referred to as RC circuits. Recall that the capacitance is C equals Q over V, the amount of charge a capacitor can hold per volt. Okay, so capacitance is Q over V. That's the maximum amount of charge that the capacitor can hold. Therefore, the voltage across the capacitor equals Q over C, the amount of charge we actually have on the capacitor divided by the capacitance. But at the moment the switch is closed, the capacitor hasn't started charging up yet. There's no charge on the capacitor initially. So the instant we close the switch, T equals 0, okay, there's no voltage here. But, okay, so across the capacitor, therefore, yeah, the T equals 0 seconds, VC equals 0 volts. Due to Kirchhoff's loop rule, we know that the voltage supplied by the battery must equal the voltages across the resistor and the capacitor. V battery equals VR plus VC. So whatever this is supplying, if it's 10 volts, then this guy could be 10 volts, this guy could be 0 volts, this guy could be 0 volts, this guy could be 10 volts, VR could be 0 volts, VC could be 10 volts, or VR could be 0 volts, and VC could be 10 volts, or that's what they said, or VR could be 10 volts and VC could be 0 volts, or they can both be 5 volts, or one could be 7 volts, the other one could be 3 volts. They've got to add up to whatever this is the whole point. Okay, here I'm using VB over here. The diagram uses E for, I guess, EMF. Okay, but it's a voltage. These are both voltages. Voltage from the power source. Okay, VB stays constant. Therefore, as the capacitor charges, so as time goes by, more and more charge will build up on the capacitor. More and more charge building up on the capacitor. Now VC isn't 0 anymore. It's going to start to increase. But as the voltage across the capacitor increases, the voltage across the resistor must decrease. Okay? As the capacitor charges, the voltage across the capacitor increases. As the charging process continues, it slows because more and more repulsive and negative charges, electrons, are being added to the plate. Okay? So you see, this is the charging process here. This is time. As time goes by, okay, we've got the maximum voltage up here. This is the voltage across V on capacitor. So it goes up, but then it starts to get more and more flat. Because early on it's easy, because there's not that many electrons on the plate. But now it gets harder and harder, and you're using more energy and more time to force more electrons onto that plate. And that's energy the battery's providing to do that. Okay, at T equals 0, we have VR equals VB, and VC equals 0. It's a very point we close the switch. The voltage across the resistance is equal to the voltage across the battery, and there is no voltage yet across the capacitor. The current I in the circuit is going to be equal to the voltage across the resistor divided by the resistance. V equals I times R, I equals V over R. So the current goes as the voltage across the resistor. When the switch is first closed, we've got maximum voltage across the resistor, we got maximum current. But as time goes by and the voltage across the resistor falls, as the voltage across the capacitor increases, then I is going to go down as well. Okay, I is going to go down as well. As time passes, VR and I decrease while VC increases. The voltage across the resistor and the current decrease while the voltage across the capacitor increases. For a charging capacitor, these are the equations we have. So VC equals V0, 1 minus, this is Euler's E, 2.718, a bunch of other numbers out here, to the T, how much time has passed, divided by RC. RC is called the time constant. Okay, it's the resistor times the capacitor. Okay, now look at how this works. At T equals 0, okay, you put a 0 there. Time T equals 0, this is 0 right here. That guy's 0 on top of that T right there. That's a 0, okay? Make it bigger. There we go. So this is T equals 0. I thought I had some more cool things I could do with this. Okay, so this T right here, this T is T equals 0. Right here. This is 0. Okay, so anything to the 0 is 1. So it's going to be e to the 0. So that e to the 0 is 1. And what do you have? You have 1 minus 1. What is 1 minus 1? 1 minus 1 is 0. So 0 times V0, the voltage from the battery, that is going to be equal to 0. So VC is 0 at T equals 0. Okay? Let me try that again. So when we first close the switch, T here, this guy here, is 0. So anything to the 0 power is 1. So e to the 0 is going to be 1. 1 minus 1 is 0. 0 times V0, the voltage from the battery, is going to be 0. So at time T equals 0, VC equals 1. Now, when we put a 1 in there, then e to the minus 1 over RC, this is not going to be 0. I mean, this is not going to be 1. It's going to be something less than 1, but it's going to be some number. So it's going to be 1 minus something, so we get some non-zero number here, okay? As we get some non-zero number here, then you're going to get a voltage across the capacitor. If we make T very, very, very big, this thing here becomes close to 0, because e to the minus this. Okay, so T time becomes large, then e to the minus T over RC becomes very, very small, approaching 0. If it gets to close to 0, then this is V0 times 1. And that means VC has become equal to V0. We're way up here now. We start at 0 at time T equals 0. We charge up to some large value that's close to practically being equal to the voltage across the battery. As for the current, okay, at T equals 0, okay, this whole thing would be 0. E to the 0 is 1, so you've got 1 minus I0. So then we have the maximum current. But at some time later, okay, this is 1, okay, this becomes a small, it starts at 1, but then it becomes a smaller and smaller number as T goes up. E to the minus something that's increasing is going to give us smaller and smaller numbers. So it gets close to 0 pretty soon. T gets so big, this number here gets very close to 0. When this number gets close to 0, you got something close to 0 times the I0. Okay, that means that I is going to go to 0. Okay, I got it in the next video. I'll talk more about this. I noticed there's stuff in there that for some reason doesn't get covered very well. So now, usually we write tau equals RC. The resistance times the capacitance, tau equals RC. So VC, the voltage across the capacitor, this is for charging. Now we have minus T over tau, okay? So we just replaced RC with tau. That's all these are. They're the same as these guys, except instead of seeing RC and RC, you see tau, okay? And I got them right off of this guy. They're right there, okay? Now for discharging the capacitor, now VC starts off at the maximum, equal to the voltage from the battery. But then as time goes by, okay, VC is going to decrease. So at T equals 0, okay, that's T equals 0 right there. at t equals 0, this whole thing is going to be 1. So Vc equals V0, the voltage from the battery. But then as time goes by, this isn't 1 anymore. This becomes 0.9, then 0.8, then 0.7, then 0.6. As that goes up, this becomes less than 1. So less than 1 times V0, Vc is going to become less and less and less until this becomes something close to 0 as time increases more and more. We're discharging now. This is charging over here, so I should put a discharging one in there. Maybe for the next video for tomorrow night, or for Monday morning, I guess it would be. All right, and then what happens with the current? So at t equals 0, it's basically the same idea. So when the capacitor starts to discharge, here's what you got to remember: it's discharging, and so you put some kind of short here, so we can go back. I'll put in the next video I'll put something up to show that. We do have it someplace. I'm not going to go look for it right now. Okay, now, oops, is that the end? That's the end. Okay, so now let's just do the problems that we can do. You've got a problem with that. For some reason, I don't have a problem where I have to actually use the E to thing. So let's see. The timing device in an automobile's intermittent wiper system is based on the RC time constant and utilizes a 0.500 microfarad capacitor and a variable resistor. Over what range must R be made to vary to achieve time constants of 2 to 15 seconds? So you're talking about a wiper. So I guess this is normal, the type of thing you would have in a car. Okay, from the equation T equals RC, we know that we just solve for R, so we want it to go from 2 seconds to 15 seconds. The capacitance doesn't change; it's a variable resistor. So when you switch the little knob to change the rate at which your windshield wipers are wiping back and forth, you're changing the resistance of the circuit. So tau equals 2 seconds up to T equals 2 seconds up to T equals 15 seconds. Remember, tau equals R times C, so R equals tau over C. So you have 2 seconds divided by the capacitance, 5 times 10 to the minus 7 farads, and you're going to have, you want 4 mega ohms for one resistor. Then the other extreme, you're going to go 15 seconds divided by that capacitance, or look at that, 3 times 10 to the 7th ohms. So therefore your range that you want to be able to move your thing back and forth would go from 4 times 10 to the 6 all the way up to 3 times 10 to the 7th, or 400 to 30 megohms. Okay. Now, the duration of a photographic flash is related to an RC time constant, which is 0.100 microseconds for a certain camera. If the resistance of the flash lamp is 0.0400 ohms during the discharge, what is the size of the capacitor to supply its energy? Okay, so we've got the they've got that little R there. Why are they? Wait, hold on a second. Hold on. Okay, this is a mistake. This should be tau right here. Tau. Tau equals R times C, so C equals tau over R. And C, that's tau right there. That's the RC time constant. That's tau. There it is. Times constant, which is 0.0. So that should be tau right there. Okay. I don't know if I can change it right now. Very easy. Hold on. Okay, I can't change it here. I have to do something. I'll have to go over to this and redo it over here in Word, and then copy it over because PowerPoint, making an equation is horrible in PowerPoint. Where am I? I'm not even in PowerPoint. What am I doing? Oh, I'm in this. Okay. So this should be tau. So you go tau to 1.00 microseconds, or 1.00 times 10 minus 7 seconds, which is 0.100 microseconds, times the resistance equals 2.50 microfarads. Then tau equals R times C. So this is B now. What is the time constant for charging the capacitor if the charging resistance is 800 k ohms. So tau, the time constant, the RC time constant, is equal to 8 times 10 to the 5th ohms times 2.5 times 10 to the minus 6 farads, or 2 seconds. Okay. And then this one here. What is the initial current? There's stuff missing here. Hold on a second. Okay, the whole problem didn't get copied over. A 500 ohm. So I'll tell you what we'll do. Here you can see how it goes. This problem turned out to be too complicated. I was going to start to try to do this one, but it's too much. What I want to do is get one like you guys have for your. Here, I'll just show it to you. You guys have this one. Which one is it? You guys have this one. So after 2 time constants, that would be 2 tau. So in other words, what you're putting in there, if you go back to our equations here, let's go over here. I know where they are. You're over here. We go to this guy. Okay, 2 time constants. T equals 2 time constants. So all you do is you put 2 tau. In other words, T equals 2 tau. So you put 2 tau in there. Well, what happens? The taus cancel. You got e to the minus 2. Okay, e to the minus 2. So when we look at the solution here, you got e to the minus 2. Okay, once again, to just talk about it again, you are, it says 2 time constants, 2 times tau. T is the time that passes is equal to 2 times tau, and tau is r times c. Okay, so what you do is you put 2 tau there, the taus cancel, you have e to the minus 2. And then that is what this is doing here. 1 minus e to the minus 2. So the voltage, the percent of the voltage of the total voltage, the voltage you have now across the capacitor, is now at 86.5%. The capacitor is charged up to 86.5% of its final value after 2 time constants. Okay, I'm going to have to come up with more problems, a couple more problems where I'll show you how to use this E. For some reason, your Roan doesn't have it as much as the old book did. That's why I keep getting confused. Where are all these? Also, I was wondering where are all the problems where you have to do series and parallel combined. There just aren't many problems in your Roan that have you doing that. So probably won't have any on the exam either. In other words, you have series, you have parallel, but you also have circuits. Here, I'll show you. See, this is in the textbook. This is under resistors and series and parallel. So you've got series and parallel all together. But there's no problems. There's not really any problems to show you how to do this. All they're showing you to do is, you got these are in parallel, these are in parallel. So you get the parallel equivalents for those guys. There they are. These two are now in series. So now these two are now in parallel. So you do parallel to those two. These two are now in series, and then you got one by itself. For some reason, there's no problems that are this complicated. They do a problem here, but the problems, they don't give us many problems to do that are like that. Okay, so maybe I'll have to come up with one that's just to show you what's going on with these guys. It won't be complicated like this one, but yeah, the problem. Of course, the other book I used to use, you'd probably have to pay like $100 for it, but this is free, so that's why I went with this. But it is missing stuff I'm used to covering, and then the same thing with the problems when it comes to the circuits with capacitors. Okay, so yeah, so they've got their sample problem. Well, even in their sample problem, they don't have you go e to the minus whatever. They don't do it here either. I don't know why they don't do that. Okay, well anyway, so just a couple of things. I'll try to remember to set up a Zoom meeting for 12 noon on Monday. The exam is on Tuesday, and it covers whatever we stopped, whatever came after the exam 1. It'll be on Tuesday. I'll give you the 3 hours, and I'll put up another video tomorrow night. So you want to get the updated version of PowerPoint. You guys don't have all this stuff here because I just did it today. and also if you haven't done it already, and then also let me think. You'll have an updated version of this guy. I'm gonna not add problems, but maybe, I mean, not add problems that you have to do, but maybe problems that we do as over the internet that I do here. And then I think that's everything. God, it's been, oh my God, it's been half an hour. All right, this is going to take a while to upload, so I'm going to start uploading it now. I'll upload this stuff here, and I'll start uploading the video after that. So I'll talk to you tomorrow, and then maybe talk to you Monday if you show up for the Zoom meeting. Night.